Today's webinar is entitled Insights into Australia's Future Climate from New Global Climate Models. Our presenters today are Hub researchers Dr Michael Grose from CSIRO and Dr Sugata Narsey from the Bureau of Meteorology. Michael is a research scientist at CSIRO working on regional climate projections, regional climate processes, attribution and projections. He has a strong interest in climate research and communication on topics with impact, acting as lead author on the IPCC 6th Assessment Report and the biannual Australian State of the Climate reports. Sugata is a research scientist at the Bureau of Meteorology, working on topics in climate change, variability and extremes, with a focus on the dynamics of rainfall. So Michael will be starting off our presentation today, after which he'll hand over to Sugata. So we might delve straight in, so I'll pass over to you now, Michael. Thank you.
Thanks very much, Sonia, and thanks to everyone for joining. So extra points for anyone who can name the city or street in that photo. Just a hint, they're not Melbourne trams. That's a little extra activity. So to give today's webinar, we'll follow the following outline. I'll give a little bit of a background into CMIP, which is the Coupled Model Intercomparison Project. Then talk about what's new, and that includes the new framing of the future using two different dimensions, socioeconomic and emissions pathways. Then I'll describe some work we did for a publication that's now out on what the new set of models is producing for Australia at a general level, overview of the results, the evaluation of how they simulate the current climate, and then just a special focus on a couple of aspects of the projection. There's a lot of other aspects covered in the paper that I won't have time to cover, so we'll just focus on a couple. I'll then hand over to Sugata to talk about monsoons and Northern Australia in detail, and just to emphasise that any one of these topics really needs this detail look. So I'll just be trying to give an overview, but then we'll have a detailed look at just a couple of topics. So just as the big picture, what is a global climate model? What does it look like? Well, this is a kind of a schematic, a visualization of what a modern global climate model would look like. In reality, it all exists in computer code on a computer, but if you were to kind of visualize it, it would look something like this. So it would divide the Earth into a series of grid boxes or cells, both in the atmosphere and the ocean. And then within each grid cell, there's a set of representations of the real world as mathematical equations and parameterizations and things like that. And then it's run in simulation mode to kind of simulate the interaction between all those different elements and the movement of the fluids in the atmosphere and ocean, but the interaction with the land, ice, and so on, to produce a total simulation of the world's climate. And that's run every couple of minutes as a time step, but then run forward for many years to produce a simulation of the climate and then test how it reacts to different scenarios of future climate change. So that's roughly what they kind of look like and what's in them at the high level. But they've obviously gone through development over time. So here's a little schematic from the IPCC Data Delivery Centre, just a look at going back through what the models were that were used into the IPCC assessment reports. So as far back as 1990, 1995, the first assessment report and second assessment reports, they used different climate model inputs that were produced around the world for that purpose, but they weren't organised into this CMIP process yet. For the third assessment report, the outputs from CMIP, Coupled Model Intercomparison Project Phase 1 and Phase 2 were used. Then CMIP 3 was used in the 2007 assessment report. There wasn't actually a CMIP 4, so you might have thought, what happened to that? It never really became public. CMIP 5, Phase 5 was used in the 2013 IPCC assessment and surrounding research, and the emerging set is called CMIP 6, and that will be used in the 6th assessment report and a lot of research around climate change from this year onwards. in the 90s and so on, models looked quite different. They were very quite coarse spatial resolution. At least 2.5 degrees was common, 2.5 degrees latitude and longitude. They employed quite different ways to simulate the climate. They did a process called flux adjustment to kind of force the climate to look like it really does. And the oceans were very simply represented as slab oceans. Through time, they've moved towards ever finer spatial resolution. They've gotten rid of flux adjustment because they feel that the models can stand on their own 2 feet and can kind of represent the climate realistically without forcing that adjustment. The ocean is fully simulated and linked to the atmosphere, and they've introduced more and more Earth system elements. So that means things like vegetation and other aspects of the land and how it interacts with the atmosphere, how carbon cycle and carbon processes move through all the different elements of the system. And the number of models has increased dramatically through time. There was 15 models included in the 3rd assessment report, 23 for AR4, 4th assessment report. There was up to 56 models used for the 5th assessment report. Not all of those were available for all of the future scenarios. Some of them were specialised for certain things or just for certain purposes. So there was usually about 40 to 45 available to produce projections with. CMIP 6, there'll eventually be over 90 models from 19 different countries available. And not all of those, again, for all of the scenarios. Some of them are for certain purposes, but there will certainly be a lot available for making projections with. Because CMIP 6 is not just future scenarios, this little kind of CD looking diagram shows the kind of core, which is the evaluation and base and kind of main simulations in the middle for kind of looking at how well the models do. Then there's a ring around that, the historical simulation, which is one of the kind of core simulations that all modelling groups need to do. That's a simulation of the historical climate that's to evaluate models and look at past changes. But from there, there's a whole range of different activities that are done with different focus areas. So from simulating the paleoclimate, regional phenomena, looking at the effects of different model choices to do with the resolution and so on, and then other more experimental ones like looking at decadal prediction, see if we can predict exactly what's going to happen over the next decade and so on. Here we're just talking about the historical simulation of the past climate and then future scenario simulations under the different scenarios that are laid out. And just to let you know that these aren't like weather models, they're not set to today's climate of today and then run forward to predict exactly the sequence of events over the coming days, months and years. They're free running climate models. They're used to assess the response of the climate system to changes like greenhouse gas emissions and so on. So the new structure that CMIP 6 will be run, the future scenario part of CMIP 6 will be run using is in 2 dimensions, and the previous generation was done for the representative concentration pathways, RCPs. This time there's a new set of a new dimension, which is the shared socioeconomic pathways, and they are in 5 broad categories, and you can see those as on the labels of each of the top of the graphs in this kind of matrix here. They involve different assumptions about which way the world will go in terms of population, technology, conflict, and many other aspects. And so they describe quite different futures. And I was thinking, what's a good way to explain what these kind of look like? And I thought, oh, can these be, in a very general sense, related to some of the more, some of the kind of future science fiction novels you might be familiar with. So perhaps the SSP5 fossil fuel development could be similar to this book, which I haven't read, called Carbon Dreams. Regional rivalry, there's a few novels about future of war and conflict and rivalry, where China and US escalating tensions, etc. And then you might be familiar with this one. There's a lot of science fiction novels about inequality and ongoing kind of division between rich and poor and the effects that has. There's fewer about sustainability, but I've heard that this novel is a bit optimistic about the future. And there's very few novels or movies about just a middle of the road future. That's perhaps not so dramatic. But anyway, that's just a little fun kind of test example of what kind of futures these SSPs might kind of look like. Which SSPs here, the socioeconomic pathways, can lead to which representative concentration pathways, which level of greenhouse gases? Well, some are seen as possible, some are seen as impossible. So, for example, under a fossil fuel development SSP pathway, you can reach quite high levels of climate forcing or greenhouse gas emissions and concentrations. That's the kind of top right box there. It's actually not possible to reach those very high levels if we follow a middle of the road sustainability kind of SSP. And similarly, it's only possible to reach kind of the very low level of greenhouse forcing or kind of greenhouse gas emissions following some of the SSP1 kind of world, the sustainability. So there's the most likely ones are kind of along the diagonal, but some of the off diagonal ones are also seen as possible. And you can see on the right hand side where the previous RCPs, which were just done on one dimension, kind of sit. So there's going to be a lot of opportunities to explore this space given the new climate simulations to do with which socioeconomic futures the world follows and which kind of physical climate change scenario that kind of or effect that has. This will be an interesting thing to see over the next couple of years. So there's of course interest about CMIP 6, what it's saying for Australia and what it's producing. Is there anything new and useful? Are these models any better than the previous ones? And do the projections agree or disagree with CMIP 5? So we thought it was important to critically evaluate what they're saying and what's new, what's different. However, CMIP 6 is only really just becoming available, so there's a real crunch in the deadlines, but we decided to form a kind of a rapid response team and look at what was available at the end of last year, which is the deadline for studies that could then be included in the IPCC report. And we brought together people from the Bureau, from universities, and from different parts of CSIRO to have a quick look at what was available at that time and have an assessment, because that would be useful and for Australia to know. Just to be clear, we looked at a set of up to 37 CMIP 6 models, not the full however many there's going to be in the fullness of time, so 60 or more. This includes 2 Australian contributions, this coupled model and the ESM, the Earth System model from Access. And we also compared that to a set of simulations from CMIP 5, and that included also 2 Australian contributions using Access. So who contributed to the rapid response team? We had a group of researchers looking at the mean climate evaluation and change. We had a special group looking at extremes mainly from the University of New South Wales and the Bureau. We had a couple of people helping with this. We've managed the data, which is an important part from University of Melbourne and CSIRO. We had a special look at climate sensitivity and temperature. That was led by myself and Julie Arblaster from Monash. Dynamic sea level, a couple of CSIRO contributors looking at that aspect. Marine heat waves, which is a really important topic, getting a lot more attention these days, which is great. A couple of contributors from the University of Tasmania. A really special, good and in-depth look at the main drivers of Australia's climate variability. That's the El Nino Southern Oscillation, the Indian Ocean Dipole, and the Southern Annular Mode, with researchers from the Bureau and CSIRO and universities all looking at that. I won't cover that much today. That's really worth its own kind of seminar and look, and that's really good work, and check out the paper on that work. And I was mainly acting as kind of a air traffic controller for all these really smart people contributing all this great work and bringing it together. So just to give you the big picture message up front, the RCP SSP structure will provide useful new opportunities, including for Australia, to explore future space. The models show incremental improvement in the simulation of the current climate and some reduction of the long-standing biases that affect our confidence in their simulations. Things like the cold tongue bias, that's how the oceans of the Western Pacific are simulated. There's an improvement in the simulation of these major climate drivers and their effects. That's ENSO, IOD, and SAM. And there's new simulation and improved simulation of some ocean features and processes to do with marine heat waves and regional dynamic sea level. I won't go into detail a lot of these, but just that's the big picture conclusion we came to. But just kind of emphasising that's incremental improvement. We haven't solved, the modelers haven't solved all the problems, and the previous generation, it's not that different from the previous generation, but there's just ongoing incremental improvement in these aspects. Temperature projections are a big new issue. There's a group of hot models, and I'll get to that soon. Extremes projection is broadly in line with previous modelling, but there's some new nuances there. And rainfall projections are similar to last time, but with a few important insights that'll need some detailed work to really make the most of, but it looks like it's likely that southern Australia, there's still high confidence in ongoing drying for southern Australia, but with perhaps new insights there. Northern Australia, the range of projected change is narrower, but a more refined knowledge of what causes the change, and Sugata will go through that in detail. So just as an example of an evaluation plot, this is sea surface temperature for summer through to autumn, and the bias in the average of all models with a little dot put where there's kind of quite a high level of model agreement on that pattern. And you can see the previous generation on the left, the new models on the right. The picture looks pretty similar. I mean, there's some areas where you kind of would say, oh, there's a little bit of improvement, so perhaps a little bit less of a cold bias in parts of the Pacific. And there's some areas where, well, that's actually new, interesting new problems, like more of a warm bias in the Indian Ocean. So yeah, that's what we mean by incremental changes. It's not a radical shift, but there's some important areas in which that reduction in that bias will be important. So getting to one of the big hot topics, literally hot topics, climate sensitivity is a very important measure of how much the Earth responds to a forcing, in this case greenhouse gases. And we had a look at the ECS index, Equilibrium Climate Sensitivity, which is a standardized measure of how much the Earth's global average surface temperature changes if you double the amount of carbon dioxide in the atmosphere. There's been much discussion, debate, and research over many years to identify this number. And for example, there's a little screenshot of a paper from 1896 on the influence of carbonic acid in the air on the temperature of the ground, which had an estimate of this value. So that's how long this kind of area has been looked at, and it's ongoing. So this is a very busy diagram, but this summarises the different estimates of the ECS index through time, starting from that Arrhenius 1896 paper in the top left, through different estimates through time. Some of them are lower, some of them are higher. The grey band summarises the best estimate of the likely range of what we think that ECS, Equilibrium Climate Sensitivity, is between 1.5 and 4.5 degrees. It was used in the last IPCC assessment. And you can see the bars show which each study kind of puts the estimated range of ECS is. Some of those are quite low. So there's a couple of ones from perhaps pretty well-known figures like Richard Lindzen trying to show that it's very low. There's some which include values that are really quite high, up at 6, 8, or even 10 degrees, which seems insane, but that was seen as possible using the analysis in some of those studies. But you can see there's a whole lot of agreement that it's somewhere in the range of 1.5 to 4.5 degrees, or perhaps maybe more likely 2 to 4.5 degrees. But this is an ongoing research area, and it will need more work over more years to really nail it down. So CMIP 6 has a group of models with high climate sensitivity, with values above that 4.5 degree likely range, but they are still below the 6 degree level, which was seen as very likely to be less than 6 degrees, or 1% chance of being above it from the last IPCC assessment. This high climate sensitivity is often driven by how they simulate clouds and certain climate feedbacks. And this little plot on the right shows a kind of a distribution of where the models sit as of, I think it was last week. This is from Gavin Schmidt at NASA, GIS. He put this up on Twitter, and he labelled the groups, the Russians, the bottom, that's 2 models which are got quite low values, down near 2. Then the pack, he called them, with 20 models sitting in the kind of previously estimated range, and then this group of high climate sensitivity models, which he named the wolf pack. I don't know if that terminology will catch on, but that's what he was labeling them. So these include models with values of up to 5.6, which is much above the hottest one from CMIP5. So the big question that's being hotly debated right now, are these plausible? Are these high values plausible, and should they be seriously considered? Well, high values up to 6 can't be ruled out yet by observed changes. They might be in the next couple of decades if we get a clear signal without any volcanoes. We can really kind of look at the observations and can narrow in that high end range and give it an upper end. Simulation of what happens in the 20th century suggests that perhaps it's too high, and there's also paleo evidence coming through suggesting it's too high. However, that's not conclusive yet. It still needs further work. I'm kind of just labeling them kind of the drag race models rather than the wolf pack here. We put out an article on Monday in the conversation about this topic, so you can check that out as well. And what does that look like in terms of temperature projections for Australia? Well, here's one of the kind of plume plots or kind of time series plots through time going into the future that we included in the study. And you can see the newer models in darker red and the older models in kind of paler colours for both an ongoing high scenario, RCP 8.5, or the new SSP 585. And you can see the upper end is higher, and that's largely driven by this group of models which have that higher climate sensitivity and a hotter temperature projection, and the higher end is higher. It's less obvious, but it is still there for the lower scenario. The hotter end is a little bit hotter still, but it's obviously less clear. So for example, using the models that were available, SSP, the high one, the range was 2.5 to 5.1 in CMIP5, and the CMIP6 so far was 2.7 to 6.2. That's the 10th to 9th percentile range, and the average was a bit higher. So this is an important new set of results that'll need to be grappled with. Yeah, just pointing out those are the Wolfpack / hot rod models. And what does that look like for an individual model? So here's an example of the Canadian air system model, previous version, time series shown, and then the new one showing the higher sensitivity and higher projection. And it's really expressed through the last part of the century more clearly. You see that difference emerging. What does it look like globally? Well, Australia is projected to be hotter in the mean of CMIP6 compared to CMIP5 so far, but the difference is pretty extreme in some other places. So for example, the Arctic, rather than a projection of something like 8 degrees, there's now a projection of up over 12 degrees. It's pretty crazy. And the difference just between those two panels is shown on the bottom there, showing where the biggest differences are, including an area of cooler projection for the North Atlantic, suggesting that the Atlantic ocean circulation may actually decrease more in the new models than in the previous set. Extremes are pretty much in line with CMIP5 in terms of their nature and their spatial pattern from the models that we could look at so far, but higher in magnitude. However, it should be noted that the models that were available to look at for extremes at this time were a lot of the hot models, so you'd very much expect these higher values. Going to rainfall, the projection from the previous set and the new set for winter and spring is shown at the top with, again, dots where there's high model agreement. And you can see it's pretty similar across Southern Australia and Eastern Australia. The colours are a little bit different in Northern Australia, but there's not very high model agreement on those changes anyway. The time series graphs at the bottom show that Southern Australia is still projected to get drier, and Northern Australia there's a lot of uncertainty, but it's the low rainfall season. And Southern Australia as a whole has a similar model mean projection, but perhaps a slightly reduced range. So perhaps there's more agreement on the likely kind of ballpark range of what rainfall change could be in Southern Australia, with some of the really dry and the kind of little change models, part of the range dropping out. Moving to the northern wet season, or summer and autumn, again, the regional pattern is pretty similar between CMIP5 and CMIP6 in terms of the projection. I should mention this is the high emission scenario in the far future, so to get a really good sense of the change signal due to climate change. So where's the differences, the important differences? Well, perhaps Northern Australia is a slightly constrained range, rather than being, well, could be a lot wetter, could be a lot drier, could be, well, minus 10% to plus 20%, rather than minus 20% to plus 20%. It seems to be what's coming through, but there's a lot more to dig into here. So this is where I'm going to hand over to Scott to really dig into the Northern Australian rainfall projections and the reasons behind it. So I'm going to stop sharing the presentation and hand over to Sugata.
Fabulous. Thanks, Michael. And we'll get Sugata's sharing up and running in just a moment. Just a reminder while we do so that there is that chat box there that a lot of people have been posting comments and thoughts. Remember to put your questions in, and we'll cover all the questions for both presenters at the end. So just hold tight with those questions, pop them in the box, and we'll get there in a moment. And over to you, Sugata. Thanks.
Thanks, Sonia. Thanks, Michael, as well. That was really good. And I hope everyone can see my screen. Can you see that, Sonia, Michael? Yep. Okay, great. All right, so as Michael said, I'm going to go into a bit more detail about the climate change projections for Northern Australia. And I'm going to try and keep this at a very sort of general level. Please, if I start to descend into jargon, start putting some questions in the question box, and Sonia will prod me probably if I get too out of control. But first, I'm going to begin with an outline of what the Australian monsoon is. So just a bit of context for this regional projection and why it is so difficult to make climate change projections there. And then I'll tell you a little bit more about what climate models tell us about the north of Australia. And here I'll just give you some summary points before I begin. So the first thing that I would like to point out is that climate models really disagree on changes to the rainfall in the north of Australia. And to the tune of, in CMIP in the previous ensemble, that was to the tune of a decrease of 12% all the way up to an increase of 8% for every degree of global warming. So that's quite a wide range, given that projected change in temperature was sort of up to 3 degrees or so or 4 degrees in the high emission scenarios. But the good news here is that the range in climate change projections for Northern Australian rainfall is actually reduced quite substantially for Northern Australia in the new model, so in the CMIP ensemble, with a range of about a decrease of about 5% all the way up to an increase of about 6% for every degree of global warming. So, you know, that's not it's not trivial, but it's a much reduced range compared to the previous ensemble. And so that's the good news. But unfortunately, we really do not have a clear indication of what direction of change is most likely with global warming. And I guess that's the elephant in the room, is that we really need to know to first order, is rainfall going to increase or decrease when you increase greenhouse gases in the future, assuming an increase in greenhouse gases. And so this study that I'm talking about today is an attempt to take a first step in that direction, which is to try and understand, you know, why do these climate models disagree on rainfall changes over the north of Australia, and what's different between those models? Okay, so without further ado, I'll just get into that. And I'll start with a description of what the Australian monsoon actually is. So here we're talking about a region over the northern parts of Australia. And for those who are familiar with Northern Australia, they get most of the rainfall there between the months of about November and April. And really, you know, in substance, mostly in sort of late December to mid-March. And you can see here I've showed you these are the monthly average rainfalls for the globe, and just for this particular region. You can see in January, the Northern Australian rainfall is actually part of a much larger system. So this band that stretches all the way from the Indian Ocean right across into the Pacific. And then in the austral winter, so when it's summer in the northern hemisphere, those massive rain bands migrate into the warmer hemisphere. And so you can see here that North of Australia gets almost no rain during that time. Right, so the point I was just going to try and get across here is that the Australian monsoon is not this thing that operates in isolation where local conditions are the only thing that matters. It's actually part of this much wider system. And so climate models are a really good way for us to try, in fact, perhaps the only way for us to really try and understand how these monsoons may change in the future. Because the Australian monsoon, like every other monsoon, is a very complex system, and it involves interaction between continents, land surfaces, oceans, and the atmosphere as well. So having said that climate models are perhaps the best way in which we can try and understand the future of Northern Australian rainfall, and Michael has given us a pretty good rundown of what climate models are and how they work, let's have a look at what climate models actually tell us. So these are rainfall projections for the north of Australia with global warming. Sorry, excuse me. And here we've got, in every bar here is a different climate model, and I've ordered them from the largest decrease to the largest increase. And you can see here that the largest decrease is on the order of minus 12% change in rainfall per Kelvin. This is for the high emission scenario for RCP 8.5 and SSP 8.5, for those who know what that means. It's a high emission scenario, and I'm showing the change by late 21st century. And what you can see here is that these models simply do not agree on how Northern Australian rainfall should change. This is rainfall averaged over land in that box that I showed in the previous slide, by the way. The other thing I'll point out here is something else that I said in the summary slide, which is that if you look at these bars here, there's orange bars and blue bars, and the blue bars are the previous ensemble models, so CMIP 5 models, and the orange bars are the newer models from the CMIP 6 ensemble. And you can see here at the ends of this graph that, in fact, there are very few models right at the ends that are orange, and so the two largest decreases were from CMIP 5, and the same is true on the high end for the largest increases. So the range in projected changes for CMIP 6 is actually a lot smaller than for CMIP 5. So that's good news. But really we need to try and understand why these models disagree before we can try and come up with a reduced range in projections. So we really want to narrow this to at least tell us, is it going to go up or down over north of Australia? All right, so let's try and do that, and that's what this study is about that I'm discussing today. We try to determine the differences between these two ends of the spectrum using something called a composite analysis. And so before I keep going, I've got to explain what that little bit of jargon means, and apologies to those who are very familiar with this technique. I'll try and give you a very simple example of what a composite analysis actually is. So here we have a rainfall decile map for Australia, and this is the winter and spring of 1982. And for those who are not familiar with these sorts of maps, red here represents drier than average conditions, and blue represents wetter than average conditions. So in the winter and spring of 1982, it was an El Nino year, and you had much drier than average conditions over much of the eastern part of Australia. So I have a simple question for you. What part of this pattern do you think is related to El Nino? And we're going to try and address that with a composite analysis. Okay, so let's try and take a look at another El Nino year. Here we've got 1991. This is another El Nino year. And so you can see the pattern is kind of different for the second El Nino year that I'm showing you. You do still have more of this red on the eastern seaboard, but not so much in the south. So just from these 2 years, you can probably take a guess that some part of this pattern that we're seeing is to do with El Nino, and some part of it is noise or to do with other climate drivers. So what if we take a couple more years as examples? Here we've got 1994 and 1997. Well, 1994 is red everywhere. It was drier than average pretty much everywhere. And you look at 1997, the signal was a bit weaker in that year. It's kind of more red on the east than it is on the west. So you can keep doing this and collect more and more El Nino years. And then we can ask ourselves what those years have in common. So here's an average or composite of rainfall deciles for those 12 El Nino years. I should say as well, sorry, these pictures are all taken from the Bureau of Meteorology's website. And so if you average these 12 El Nino years, what you end up with is the figure below, which shows that during El Nino years, on average, you seem to get drier than average conditions in the eastern parts of Australia. Okay, so the aim of a composite analysis is to take samples using some criteria and average them together so that you average out the noise, and hopefully this leaves behind the signal that you're interested in. So here you can see the signal associated with our sampling criteria, which was El Nino years. So what we're going to do is we're going to try and apply this same sort of technique to the climate models that we've got available to us, to try and understand what is the difference between these models. So what's the difference between the left side of this graph and the right side of the graph? On the left side, you have models that get dry with global warming, and the right side, you have models that get wetter with global warming. And all these models, let's not forget, these models are all given the same change in greenhouse gases in the future. So the same increase in greenhouse gases, some of them get wetter and some of them get drier over Northern Australia. We want to know why. So what we do is we take the models in each of those groups and we average them, and we look at what the mean conditions are in that group, and then we compare it against the mean conditions in the other group. So here on the left panel here is the group of models that become wetter on average in CMIP 6, wetter in the future, that is. And in the middle, you see the average of the group of models that become drier on average in the future. Again, sorry, this is the December to February rainfall here. And what you can see for these two groups of models, the first thing that stands out to you is that, these models are very similar in how they simulate the mean climate, which is really actually good news. That's something that we should find reassuring, because they simulate the major features of the mean climate. For example, the climatologically, the rainfall bands that we're familiar with, or that we've been talking about here across the Indian and Pacific Oceans. But if you compare them more closely, there are some finer details that exist, there are differences in the details that exist. So on the right-hand side, I show you the difference between the dry and wet groups. Oh, and this is again, sorry, over the historical period. This is from 1950 to 2000. And you can see that even in the historical climate, these two groups of models have some differences. So you can see that blue band across the equator is telling us that in the dry and wet groups, there's a difference in where they simulate the mean position of the tropical convergence zones. So that's a kind of interesting feature. I won't talk too much about the historical biases or differences in these models. I'll just go straight to the climate change projections in the interest of time. So here again, I do the same sort of composite analysis. And this is again showing the wet group, the dry group, and the dry minus wet group. And again, I'll just remind you, the wet group here, I'm talking about the models that become wetter in a warmer future over Northern Australia, and the dry groups is the models that become drier over Northern Australia in the future. Right, I've circled that here. So you can see for the wet group, it gets wetter over Northern Australia, dry group, it's drier over Northern Australia. But by and large, you can see that these two groups of models have on average a very similar spatial pattern in rainfall change. So there's some features there that I'll point out. There's strong wetting in the tropical Pacific Ocean and also over the other ocean basins. And that's a feature that is kind of talked about broadly and also in the Southern Pacific. But the nuance that matters for Australia is the little bit that I've circled there. When you subtract the two of them, you exaggerate those differences. So this is telling us that models that become drier over Northern Australia, sorry, on the right-hand side, that's the last panel, the models that become drier on average over Northern Australia actually become wetter than the other models on average in the Western Equatorial Pacific. So there's some sort of compensating effect there. The models that become drier over Northern Australia actually become wetter elsewhere, anomalously wetter elsewhere. Okay, so I'll just focus a little bit on the differences now between CMIP 5 and CMIP 6. And here I'm showing you just what was the rightmost panel in all those previous slides, which is if you take the dry group of models and you take their average of those and you subtract out the average of the wet group of models, so those ones that get wetter, you get these patterns. On the left here is the previous ensemble, CMIP 5, and on the right is the figure for the newer models from CMIP 6. And what we're seeing here is that models that become anomalously dry over Northern Australia in the future, so the models that get drier over Northern Australia, they actually become quite a lot wetter in the Western Equatorial Pacific compared to the other group of models. And also here we can also see that the models that become anomalously dry over Northern Australia, they also become drier on average over the other continental Southern Hemisphere land regions. So you can see here for the southern part of Africa and also for Central South America, models that become dry over Northern Australia actually become drier over these other places too. And the same, almost the same pattern pretty much is repeated here in the CMIP6 ensemble. So that's good news. There's something physically consistent happening between these two ensembles that is causing these climate models to diverge in their projections. So from this, we can kind of get the hint that there's some kind of hemispheric scale response that is kind of fundamental in these models. And we really need to understand that better if we want to decrease the uncertainty in our projections. Okay, so I'll just summarize where we got to with that. I explained a little bit about what the Australian monsoon is and how it's a pretty complex system, but climate models are one of the best tools we have available to try and understand how the Australian monsoon may change in the future. Unfortunately for us, climate models disagree on changes to the Australian monsoon. That has been a stubborn condition in pretty much every ensemble of climate models dating back, at least the ones that I've analysed. CMIP6 is no exception to that, but fortunately, and it seems to be some good news in the new ensemble, that the range in climate change projections for Northern Australia is somewhat reduced, so approximately half, which is great news. But unfortunately, we still do not yet have a clear indication of what direction of change is most likely with global warming. And that's really the elephant in the room for us here. So to try and progress this forward, we did this study where we looked at the differences between models that get wetter and the models that get drier. And we found that hemispheric scale processes are likely to control the Australian monsoon changes because of this synchronicity between Southern Hemisphere land regions. And I'll wrap it up here with a brief summary of the things as well that Michael talked about. And so Michael talked a bit about the model mean state biases and the evaluations that we did for the CMIP6 ensemble that's available. And we found that model mean state biases are pretty similar to previous generations, although there are some incremental improvements. And this is not unusual. This was the case for pretty much every new set of climate models that become available. You don't see these dramatic leaps forward, but these incremental changes, and that's a sort of slow march of progress to the science. But with the advent of CMIP6, there are many new opportunities to address questions and many different sets of experiments, aside from the ones that Michael and I have discussed here today. Projections between CMIP6 and CMIP5 are largely similar, but there's one very striking difference, and Michael touched on that, the issue of climate sensitivity, with CMIP6 containing a subgroup of models with very high climate sensitivity. And if these turn out to be accurate, and it's not clear yet whether they are or they're not, if they turn out to be accurate, then that would imply much hotter projections for the future, including for things like temperature extremes. And for the rainfall projections, we find that in general, the rainfall projections seem to be slightly more constrained than in the previous ensemble. So that's true for the North of Australia as well as Southern Australia. Yeah, so okay, we've covered really a lot of detail, areas in cursory detail, and I'm sorry that we were not able to go through everything that you might find interesting or came here looking for, but you can find a lot more information from these two papers. The first one is in Earth's Future, looking at CMIP6 for Australia's future. And the second paper was the one that details the stuff that I just talked about on Northern Australian rainfall projections. That's in Geophysical Research Letters. So I think I've spoken pretty quick, but I think we have time for some questions. And thank you very much for listening. I'll hand over to Sonia now.
Fabulous. Thanks, Sugat, and Michael as well for a great presentation. We covered a whole lot of information, and we've had in the background in the chat box a whole lot of questions and comments coming in, which is really fantastic. Some questions being asked that other people answer, and great conversation. So I'll do my best to touch on the questions that haven't been answered. and I'll try to direct them to the relevant speaker, but please feel free, Sugata and Michael, to chip in where you think appropriate. So the first question comes from Ian, who asks, is there an effort to identify which combination of SSPs and climate sensitivities are consistent with meeting the Paris Agreement targets?
Sure, yeah, so meeting the main Paris Agreement target of keeping the global average temperature at 2 degrees or less since pre-industrial, remembering we're already at 1 degree or a little bit more, is really only consistent with the very kind of most the sustainability SSP, and very and even then the model results include models that still go above that, so it's still not a guarantee. And the sensitivity, the climate sensitivity kind of value also comes into this, of course, because even if we follow a very low emission scenario, but climate sensitivity is high, that gives you a high chance of exceeding that temperature value. So it does kind of throw a spanner into this calculations of what we need to do to meet warming targets, for sure.
Great, thanks, Michael. The next question comes from Nicholas, who asks, do these rainfall results have a small enough resolution to have meaning for Tasmania?
Yeah, so Tasmania there's a lot of differences in rainfall across quite a small area, from the very wet west coast to the rain shadow area in the Midlands, and a very different rainfall regime in the northeast, etc. So it has broad implications for what is in the future for Tasmania, but there's a lot of extra value from running higher resolution models for Tasmania, because to account for the differences across the area and the topography there, and that has been done in the past, and can be done more in the future, and that definitely adds a lot of insights for Tasmania.
Thank you. And a question from Joe, who asks, is there more information on the specific feedbacks that, as well as clouds, seem to be driving the hot rods? Yeah,
I'm glad you chose hot rod, not wolf pack, so being out the guy from NASA. Yeah, so it's a big topic of research right now. A lot of people looking at it in very great detail. So the main ones seem to be around clouds, convection, and how clouds interact with particles in the air, aerosols as well, which have always been the thing that determines how big climate sensitivity is the most. So there's other types of feedbacks as well, but moisture, clouds, and convection are just a huge part of the story, especially clouds over the Southern Ocean, but elsewhere as well. But it needs more work to have a really clear picture of it.
Great, thanks. The next question comes from Jeff, who asks, are the warmer results from CMIP 6 mostly due to updates in the models or updates in the forcings?
Yeah, that's a really good question, and there seems to be some difference from the forcings. By changing to the SSP structure, they've changed the inputs for each of the scenarios a little, and that seems to have made some of the effect, some of the difference. But the higher climate sensitivity in the models is just a big part of the story. Like a higher climate sensitivity model will just react more strongly to whatever forcing scenario that is applied. And I think with more work, we'll be able to kind of quantify the exact breakdown of that a bit better.
Right. The next question is around the smaller drying in the southeast is quite noticeable. Michael, I wonder if you have seen results from more than these models or the output for the IPCC Working Group 1 Atlas. And I wonder if this will be the case when we consider all the 100 plus CMIP 6 models. The smaller range, whilst it might be by chance, is a nice news story.
Yeah, that's a really good point to make, and I'm glad someone pointed that out, is we were just looking at a snapshot at the end of last year. There's more models coming through in the pipeline, and they will also need to be considered to get a really good sense of the full uncertainty space that CMIP 6 is producing. And yeah, time will tell whether that constrained range remains or not. I have seen the IPCC Atlas results. I'm acting as the IPCC Australasian representative on the Atlas, so I'll be able to keep in touch with that. And yeah, there's going to be a new, really nice interactive version of the Atlas. And if you're interested in that right now, you can sign up to be a reviewer of it. So if you're at all interested, please do that. And that'll be a great little way to view previous models, new models, different baselines, and so on.
Great, fantastic. Another question from Ian, who says, I love the plot of rainfall changes per degree for all the CMIP 5 and 6 models. How much of the spread in projections in the CMIP 5 models is due to the 3 outlying models, GISS MK 3.6 and BNU ESM? Has there been any evaluation specifically targeted at these models?
Yeah, thanks for that question, Ian. Look, yes, you're right. A significant amount of that variation is related to those outlier models. This is something we addressed in the paper as well. If you change a sampling method and you either include or don't include those outlier models, for example, you do still end up with the same scientific conclusions. Maybe not quite as dramatic in terms of the magnitude of those patterns, but the actual patterns themselves remain. So the conclusions of this study are irrespective of how we choose to sample the models. But you're right that those models are significant outliers. I would point out as well, though, that although those models were outliers, they were state-of-the-art models at the time that they were produced in CMIP 5. And yes, there's been a lot of focus on the fact that they are outliers in some sense. But I wouldn't be quick to discount them because they're legitimate and plausible models as well. And actually, probably some of the modelers are online here. I saw Simon Marsden was on there. I don't know if he had anything to do with Mark 3.6, but he'd probably know more than I do about how much evaluation's been done for that.
Fabulous. And maybe a slightly similar question from Nidhi. Do we take the same ensembles of models when comparing CMIP 5 versus CMIP 6 models? Can the difference be attributed to this? Yeah,
that's a really good question, Nidhi. Look, we also addressed that in the review of this paper, and essentially the problem for trying to take the same models between CMIP 5 and CMIP 6 is the question of what is the same model. When you add a component, you can completely change a model. And so, unfortunately, we didn't do that. It would have been nice to be able to do that, but I think it's really difficult. And one thing that you might want to think about when we talk about that is that when you look at the full ensemble of CMIP 6 models or CMIP 5 models, they actually all share a lot of different components. So they're not really independent models in the first place. But when you go to the next ensemble, you add different components, you might add complexity. And so it wasn't clear what would constitute the same model between two ensembles. So we didn't do that. Yeah.
Okay, the next question is, are there any links between the hot rod models and the dry, wet, tropical projections?
Haven't looked into that, I don't think. Yeah, however, I mean, Sugat did look at change per degree of global warming. So if it is a matter of just a stronger warming means implies a greater change, that's actually accounted for in that calculation. So if it warms up by more, then that's taken into account by expressing it as per degree. But it still may be worth looking into, because how the model simulates that high climate sensitivity may have some relation to then other processes in the system. So it still might be worth looking into, of course.
Yeah, I can comment on that as well, if that's right, Sonia.
Sure.
Look, if you don't scale the changes in rainfall in Northern Australia by the global change in warming, you roughly come up with a similar grouping. So another way of thinking about that is that when you warm the climate, you don't just change the local conditions in the place where you care about, you actually change the conditions everywhere. And this can lead to large-scale pattern changes. And so it actually turns out for rainfall changes in any given location, or in most locations over the globe, the thing that matters is not necessarily the local change in temperature, but this change in pattern and distribution of rainfall. So imagine if you're in a place that rains a lot, and that rain band suddenly migrates a little bit east or west or north or south, then suddenly you could go from very wet to very dry. And that's kind of what we see in these climate models, is that some of them move rain bands a bit further away, and some of them move them kind of and fix them further over the north of Australia. So that's kind of more important than, in my opinion, than the climate sensitivity issue.
Mm-hmm. Fabulous, thanks for that. Kate asks, can you comment on whether CMIP 6 shows cyclones migrating south?
I can't comment. I haven't looked at that at all, but it might be worth checking the latest literature as it's coming out to see if there's studies on that yet.
Yeah, look, we do have people within the program who work specifically on that, and maybe that's something we can take on notice, and Sonia could get back to whoever asked that question at a later date.
Yeah, absolutely, great. Next question comes from Alison, who asks, do any of the models incorporate feedback stemming from CO2 fertilisation effects on forest carbon sequestration?
So there's a range of climate feedbacks in the system, and some of them are modelled in this kind of model. So including things like cloud, ice albedo, etc., including some carbon feedbacks in the Earth system models, the ones that simulate the carbon cycle and the carbon system and so on. So that will be included to some extent. But it's important to realise that some feedbacks, some Earth system feedbacks, are kind of challenging or actually aren't included. So things like the big ice sheets melting and then adding to sea level and exposing land underneath them is something that's not included. And also the release of some greenhouse gases from some types of landscapes isn't included because it's just difficult to do so. So yeah, the equilibrium climate sensitivity is a measure of all of those feedbacks that can be simulated in a model. The real Earth system sensitivity, which is what we'll see eventually after hundreds of years after a change, is a bit higher than that because of those other feedbacks.
Okay, great. Thanks, Michael. The next question, sorry, there's so many coming in. It's fabulous. The next question is, do the models take account of the melting of the tundra?
Yeah, so that's related to the previous question in some ways. So the release of methane from permafrost and so on may not be included in all models or fully in any model, I think. So that is an area in which would add to that the full Earth system climate sensitivity.
Oh, okay. The next question states, CMIP 6 models perform slightly better than CMIP 5 in the historical, but show high sensitivity. For example, NCAR CSM2 performs better than CSM1 in historical, but shows higher ECS. Is it because the models are heavily tuned to reproduce historical climate, but find it difficult to respond to CO2 forcing?
Yeah, so this is getting in pretty deep into this topic, and it's a very interesting question. And it's true in some ways the evaluation of the mean state in some of these models is improved. However, their response to CO2 is higher. So that raises questions about, you know, the effect of tuning different parameters and so on. However, some of the models that evaluate well in the mean state in the current climate, you also need to evaluate them on their trends over the 20th century and also their trends over longer time series, and that may actually not come out better than the previous generations for that, because a model is you evaluate it by looking at a snapshot of the current climate and how good that looks, but also how it responds to past changes to get a full idea of its evaluation. So those kind of work is ongoing and still needs to be done more. However, I should mention, since you raised the topic of tuning, people, the modelers, you know, do a lot of hard work and a lot of smart thinking about tuning models. They don't tune models to get a particular result. They just make adjustments in how the model is configured to make it as realistic as possible, and then run it and then see what comes out of it. They don't tune the models to get this high result. No one's trying to do that.
Great, and that's a really a really good point to make, Michael. So I think we have pretty much run out of time. Thank you for your patience. I will finish with one last question and then we'll wrap up. The last question comes from Anthony, who asks, are there any distinguishing scientific properties or features of the Wolfpack models that differentiate them from the rest of the ensemble?
Yeah, so they are the kind of latest generation of models produced by the world's leading centres. So they're serious models that need to be taken seriously. And they aren't all from making the same changes, but they are different because they've adjusted the same kind of group of changes to their things like how they simulate cloud and convection in the atmosphere. Each of the groups has done work on their model in those areas, and some of them are related because they kind of are similar between different modelling centres, but some of them are a little bit different. But they've all done similar things to their models and similar what they believe are improvements, and this is just the result of that. And yeah, sorry to keep saying this, but with further work we'll understand more.
Yeah, absolutely. All right, we are out of time. I know there were some questions that we didn't quite get to, so there are some contact details on the screen for how you can get in contact with us. If you do want an answer to your question that we didn't get to, please feel free to email us at that info@nestclimate.com.au inbox, and I'll work with Sugata and Michael to ensure that we get a response to your question. So thank you very much to Michael and Sugata again for a fabulous and really informative webinar. Thank you to all the attendees as well. I think that was our world record for attendees at one of our Earth Systems and Climate Change Hub science webinars, so thanks for your interest. Just to note that a recording of today's webinar will be provided on the Hub's website by the end of the week, and there'll be a follow-up email to all people who registered looking for some feedback on our webinars, as well as providing you with that link just in case you missed it or want to revisit some of the information covered. As I said before, if you've got any questions or queries about today's webinar or the work of the Hub, please get in touch. We'd love to hear from you. And also just a little plug for the next month's Earth Systems and Climate Change Science webinar. There'll be an email and information provided around that over the next couple of weeks, and that webinar will be held on the 16th of June. And a little bit of a different approach for this webinar, we'll be looking at using a case study that the Hub has been involved in to show the utility of climate change science data and information, and how that information can be used to inform industry level climate risk assessments and adaptation. So the case study we'll be looking at is understanding climate change impacts on mangoes in the Northern Territory. So stay tuned for some emails around that. And once again, thank you very much to our presenters and to all the attendees. And we look forward to seeing you at the next Earth Systems and Climate Change Hub Science webinar. Thank you.